right, 4.1 in their angle measures. So it tells us here the engineers in the ancient world discovered ratios within right triangles as they learned fundamental engineering skills. The secrets and patterns necessary to understanding circles and spheres helped in the development of trigonometry. Our chapter begins the journey into trigonometry with an introduction into angles and their measures. So let's first talk about some angle characteristics. And so we can see here that an angle is determined by rotating a ray about its endpoint. And so the vertex is the endpoint of the ray. The initial side is a starting position. And the terminal side is a position after rotation. All right, so remember from geometry, you learned about the vertex. The vertex is where the two rays are going to meet. Okay, the starting position is where it starts, is called its initial side, and where it ends is called the terminal side. And you can see here, looking at this, that it's going to start here at the initial side, and they draw an arrow to the terminal side there. All right, so angles that are in standard position are placed on a coordinate plane with the vertex at the origin and the initial side on the positive x-axis. So positive angles are determined by a counterclockwise rotation. Negative angles are determined by a clockwise rotation. All right, so if we're going counterclockwise, like the one they have drawn, it's going to be a positive angle. But if they go clockwise, our angle will be negative. The angle size itself would be the same if but one was a 40 degrees and one was negative 40 degrees. The positive and the negative just tells us the direction in which it's going. All right, so before we move on to the next part, though, let's just make sure we remember some of the quadrantal angle measurements here. So if my initial side is on that positive x-axis and the vertex is at the origin, and my terminal side is also in the same location there, like it doesn't move, that means that I have gone 0 degrees. Now, if my terminal side is straight up, then that means that we created this angle here. So if it's straight up, that means that angle would be 90 degrees. So what if it goes that straight line instead? What if we go all the way over here? Well, a straight line is going to have 180 degrees. But what if instead it keeps going to the straight down? So if we're going to go straight down, that's going to be 270 degrees. And if it makes a complete circle here, the complete circle is 360 degrees. Now, if we decided we were going to go clockwise, then if we're going to go clockwise here, this here, of course, we would still start with our 0 degrees. And then at the very bottom there, that would be our negative 90 degrees. As we keep going, then we would have the negative 180 degrees. Then at the top would be negative 270 degrees. And if we went the full circle, that would be negative 360 degrees. So notice they're just kind of opposite of each other there, okay? So the distance is the same. If we look at, let me pull up an eraser here so I can get rid of some of these lines and stuff I have drawn here. Okay, so if you look at the distance between these two angles and these two angles, they're both 90 degrees. Just one of them's positive because we went counterclockwise, and the other one is negative because we went clockwise. All right, so let's talk about some coterminal angles then. So it says two angles in standard position have the same terminal side are called coterminal angles. So they share the same ending side. So we can find an angle that is coterminal to a given angle by adding or subtracting one revolution, which remember, for in degrees is 360 degrees. So any given angle has many coterminal angles. For example, if beta is equal to 36 degrees, it is coterminal to all of the following: 396 degrees, 756 degrees, negative 324 degrees, and negative 684 degrees. So what they did there is they just added 360 twice. When they added it to the 36 the first time, they got this, and then they added it a second time and got that. And they said, okay, what if instead of going counterclockwise, what if we go clockwise a full circle? So they took they took the 36 degrees and they subtracted 360 degrees, and then they subtracted another 360 degrees. So what it is we can have an angle here. I'm just going to draw one in. This is just an example. Doesn't have to do with that problem there. I'm just borrowing the space. So I can have this angle here. But it's going to have the same ending side as the angle whose measurement goes all the way around plus a little more there, okay? So they're sharing this same side, so they're called coterminal angles. And we'll see in just a little bit they'll have this same reference angle. All right, but the big thing on finding coterminal angles is that you're going to add or subtract one revolution. So add or subtract 360 degrees. And so sometimes you'll see that written as it's your angle plus 360 n, where n is an integer, okay? Because remember, integers don't have decimals, but they can be positive or negative. So that's why we didn't put a minus there. So it's just where we add or subtract 360 degrees from our angle. And this right there, that symbol, that's theta. You'll see when we're doing trig here that they use Greek letters in trig, where in algebra we use like X, Y, and Z. They use like alpha, beta, they'll use delta, they'll use theta. You'll find a bunch of those different angles like that, or variables like that being named. All right, so let's move on to example 1 then. It says, draw 220 degrees and label theta prime as the angle that is coterminal. So 220 degrees, we're going to start in standard position. So my vertex at the origin, my initial sides on that positive x-axis. And so 220 degrees is going to be somewhere down here, which remember, this is quadrant 3. Let me label them real quick for us. So it's like we write the letter C. Okay, if I was going to write the letter C, I would write it like that. So we start up here in quadrant 1, then we have quadrant 2, we have quadrant 3, and the bottom right is quadrant 4. All right, but back to this problem now. So there's our angle. It's 220 degrees, that's our theta, and it wants us to find an angle that's coterminal with it. Well, let's first do it algebraically. So theta prime, if I want a positive coterminal angle, if I have 220 degrees, I can just add 360 degrees. And that's going to give me the positive coterminal angle of 580 degrees. So when I go to draw this one, 580 degrees, if I start again in standard position, with my initial side on the positive x-axis and my vertex at the origin, when I go to draw that in, I'm going to go a full 360 degrees, but I'm going 580 total, so I need to go an additional amount right here, which would be an additional 220 degrees. And so I would end right here where they share the same terminal side. So this is a theta prime. So that's a coterminal angle. But what if instead I said I wanted a coterminal angle that was negative? Well, in that case, I can subtract 360 degrees. And when I do that, I'm going to get negative 140 degrees. And so if I wanted to see what that looked like on my graph, again, I would start in standard position. So my vertex is the origin, my initial sides on that positive x-axis. This one's negative, so I'm going to go clockwise. There's negative 90 degrees, and I need to go 50 more, which is going to put me right there. So this here is also a theta prime. It's just a negative one, okay? But the point is they're all going to share that same terminal side. All right, so reference angles and methods to measure angles. It says reference angles, given an angle in standard position, its reference angle is the acute angle formed between the terminal side of the given angle and the closest x-axis. They just put the x-axis, that's really all you need for the definition, because you want it to be an acute angle. And an acute angle means it's less than 90. So if you don't go to the closest x-axis, your angle's not going to be acute, okay? So we can see here in this drawing that they gave us, and it tells us further, it says the angle at the left is 210 degrees. The reference angle is, and they want us to find it. Well, first thing, just what is a reference angle? So here's our angle. The reference angle is, it says, the acute angle formed between the terminal side and the closest x-axis. So it's this angle right here, okay? It's like a measurement. It's how far is that terminal side from the closest x-axis. Therefore, measurement's always positive. So it doesn't even matter if our angle had been a negative angle, our reference angle will always be positive. All right, so if the whole angle is 210 degrees, how am I going to find this small reference angle here? Well, let's see. We know that from here to here was 180 degrees, right? And so that 210 minus that 180 is what gives us that little reference angle, which is 30 degrees. Now, if you're looking at an angle that's between 0 and 360 degrees, I can give you some formulas to help you figure them out. So my recommendation is if your angle is not between 0 and 360, if it's a negative angle, you need to find its positive coterminal angle that is between 0 and 360 degrees. And the same thing vice versa. If it's a really large angle, let's say 500 degrees, then I need to subtract 360 to find its coterminal angle that is between 0 and 360 degrees. So if we do that, then if we're in quadrant 1, our reference angle is our angle. Okay, so if our angle had been 40 degrees, it would already be an acute angle, and so that 40 degrees is how far it would be from the 0. So it is our reference angle. If we're in quadrant 2, our reference angle is going to equal 180 degrees minus our angle. We already saw in quadrant 3 down here that our reference angle would equal the angle minus the 180 degrees, because 210 minus 180 was the 30. And if we're in quadrant 4, that reference angle is going to be the 360 degrees minus our angle. But remember, those formulas only work when our angles are between 0 and 360 degrees. Sometimes you'll get some angles that you're like, oh, I can figure this out without converting or using a coterminal angle. Sometimes we're going to need them. All right, and one other thing is if you have an angle that lies on a quadrant. Well, I'm thinking about it, okay? So let's say it comes out to be it's 90 degrees. And if it asks you for the reference angle, technically they don't have a reference angle, but when we're using reference angles and quadrantal angles to solve, we would use that 90 degrees. So you would just put 90 degrees on there, even though it's not an acute angle, okay? Same thing if it's 180 degrees. If it lies on any of these quadrants, you're going to give the angle measurement that is between 0 and 360 degrees to help us be able to find it. All right, let's keep going then. So example 2 says that we're going to draw each angle and state its reference angle. So 2A is 150 degrees. So we're going to start in standard position. 150 degrees is going to end over here in quadrant 2. So there's our 150 degrees. And we want our reference angle. So our reference angle is the angle formed between the terminal side and the closest x-axis right there. So we're going to take our reference angle is equal to 180 minus the 150, which is 30 degrees. Don't forget to put your degree symbol, okay? If you don't put your degree symbol, it's the same as not labeling. All right, 2B, we're going to start in standard position of 315 degrees. So my initial side's on the positive x-axis. My vertex is at the origin. And we're going to graph it till we get to 315 degrees, which is over here. And so we want to know, what is our reference angle? Well, we're in quadrant 4, so we can take our reference angle is equal to the 360 minus 315, which is the 45 degrees. Let's go ahead and do 2D. So 2D is 140 degrees, so we're going to put our angle in standard position. 140 degrees is going to be over here in quadrant 2. And so we're looking for the measurement of that reference angle. Since we're in quadrant 2, we know the reference angle is 180 minus 140. And so we find that it is 40 degrees. And then 2C, the negative 120 degrees. So we're going to put it in standard position. And it's negative, so we're going to go clockwise 120 degrees. So that's 90 degrees plus a little more. Okay, so there's my 120 degrees. Excuse me, negative 120 degrees. Now, some of y'all can say, okay, well, negative 120, let me draw it, sorry. This piece right here goes up to negative 180. How far apart are they? And that's fine if you can do that, do it. But otherwise, if it's negative, I'll need to make it bigger. So I'm going to add 360 degrees, which is 240 degrees. And so if I'm in the third quadrant, I know my reference angle is equal to my angle minus 180. And so I find that it is 60 degrees. Now, if you try to say how far is negative 120 from negative 180, that works. But you're probably going to think negative 60. But remember, reference angles are always positive, okay? The negative just tells us that we were going clockwise. And so that's how we find our reference angles. Now, I'll tell you that in a few minutes here when we get to some other stuff. All right, so we also have a thing called degrees, minutes, and seconds. And so we can write decimal degrees in terms of smaller units called minutes and seconds. And this is used a lot in navigation. So notice here it tells us, and I think about a clock when I do this, probably because of the minutes and seconds, but 360 degrees is one revolution. And so if I look at a clock, I know it's 360 degrees to go all the way around. So then if I want to take my degrees and change it to minutes, 1 degree will equal 60 minutes. And if I want to take minutes to seconds, 1 minute will equal 60 seconds. Or if I wanted to jump from degrees to seconds, so remember it's degrees to minutes are 60, minutes to seconds are 60, so 60 times 60 would give us the 3,600. And so 1 degree is equal to 3,600 seconds. So 3A tells us we want to convert 36 degrees, 25 minutes, and 18 seconds to decimal degrees. So if I want to go to, notice my degrees and my minutes don't have decimals in them. So this is how I can remember to do this. I want to make them smaller. So to make something smaller, I need to divide it by something bigger. All right, so we're going to keep because we want decimal degrees, so we're going to keep our 36 degrees, and we're going to add. I'm going to take and change that 25 minutes to degrees. So I'm going to take that 25 and divide it by 60. Plus, then I'm going to take that 18 seconds and I'm going to change it to degrees. Now I'm not going to go to minutes, which is the one above it. I'm going 2 above. So that's what we're going to divide by the 3,600. And so then we can just type this all in our calculator. And it should tell us 36.422. And it's in degrees. Now, for the vice versa here, if I'm going to convert 42.575 degrees to degrees, minutes, seconds, we're going to take it to degrees, minutes, seconds to get rid of those decimal degrees. So I'm going to keep my whole degree. So I'm going to keep that 42 degrees. And then I'm going to convert to minutes. So in order to do that, we're going to take the decimal part, and I want to make this number bigger, so now I'm going to multiply it times 60. And when I do that, I get 34.5, and this is going to be minutes. But remember, we don't want decimals. That's our whole point, is to get rid of the decimal. So we're going to keep that 34 minutes, but we're going to take that half a minute there, and we're going to convert it to seconds. So that point, whoops, let me write convert to seconds. So you're going to take that decimal, that 0.5, and you're going from minutes to seconds, so just multiply it times the 60, and that'll give you your number of seconds. And so 42.575 degrees is equivalent to 42 degrees, 34 minutes, and 30 seconds. Now, guys, if you're doing these and you convert it to minutes and you don't have a decimal on it, then you don't have to have any seconds, okay? You keep going until you don't have a decimal any further. All right, radians and central angles. So another way to measure angles is in radians. So in the late 1800s, mathematicians began to see a need for another unit of measure because they needed angle measurements to cancel out. This type of measure is needed in calculus to help simplify certain mathematical and physical formulas. So something to remember is radians have no units. One complete revolution is 2 pi, and we'll talk about why in just a minute. And just so you know that 1 radian is approximately 57.296 degrees. Tells us the definition of a radian is based on the concept of a unit circle, which is a circle that has a radius of 1 unit, with its center at the origin of the coordinate system. The radian measure of an angle is based on the length of the arc on the unit circle. So central angles on the unit circle. It says we use a central angle of the unit circle shown at the left with the vertex as the center of the circle. 1 radian measure of the central angle that subtends or intercepts an arc equal in length to the radius of the circle. So what they're saying here is we've got our radius of our circle. That's going to be the same exact length as the arc here. So that's why we can say that that would be 1 radian. So remember, the circumference of any circle is 2 pi r, where r is the radius measure. So a circumference of a unit circle that has a radius equal to 1 is going to be 2 pi times 1 units. Therefore, an angle representing 1 complete revolution of the circle measures 2 pi radians. And that's how we got above where 1 complete circular revolution is 2 pi radians. All right, then it tells us that if theta is a central angle in a circle of radius r, and if theta is measured in radians, then the length s of the intercepted arc is given by s is equal to r times theta. And so we're going to see this later. This is what we're going to use to find arc length. We're not actually going to use it in this section, but it's coming up. All right, so before we move on to the next thing, let's go ahead, I guess, and let's talk about, well, I'll just talk about it as we do the examples, I guess. I can add on to it. So common radian measures is a sketch each radian measure on the coordinate plane below. Oh, excuse me. So let's look at the last one there, actually. We're looking for pi radians. Well, remember, we just said that a full circle, so if we have 0 here, a full circle was 2 pi. So where is pi going to be? Pi is halfway, so pi is going to be over here at what was 180 degrees. So this is our pi. Now, just to help us, like on, well, I'll do it on the next one. Okay, so now we're looking for pi over 2 radians. Well, we know that this is 0. But we also know if we go the complete circle, it would be 2 pi. And we just said, though, if we go only half the circle right here, that this is pi. So if that is pi, where is pi over 2? Well, it's going to be that split in half. So pi over 2, whoops, well, is actually going to be at the 90 degrees. So here is our pi over 2. And then negative pi over 4 radians. Well, think about this. Let's think about where would positive pi over 4 be, okay? 1/4 is half of 1/2. So if we know that pi over 2 is right here, then pi over 4 is going to be half of that. But be careful because on this one, we're looking for negative pi over 4. So we're still going to start in standard position, but this time we're going to go clockwise that same amount. And so there is our negative pi over 4 radians. Now I'm going to go back to this first one, the first one we did, the last one here. And so we said up here at the top was pi over 2. And so we'd have 1 pi over 2. Pi would be 2 pi over 2. And down here at the bottom, the 270 degrees would be 3 pi over 2. Just so we know where they're at. And then to convert between units of measure. So our conversion formulas. If we want to convert from degrees to radians, we're going to multiply our angle that's in degrees by pi over 180. Because pi and 180 are in the same location, it's kind of like multiplying by 1, but it helps us just change from one form to the other. And then if we're going to convert from radians to degrees, we're going to take our angle in radians and we're going to multiply it times 180 over pi. And so that would change us to degrees. All right, so let's practice some of this. So we're going to convert each angle from radians to degrees or from degrees to radians. So notice our first one's in radians, so we're going to change it to degrees. So we're going to multiply by 180 degrees over pi. So remember with fractions, you multiply straight across. So we would have 7 pi times 180 over 6 pi. Well, our pi's are going to cancel, and so we're really just left with the 7 times 180 over 6, which I could just plug that then in my calculator, and it's going to tell me 210, and I need to make sure I put my degree symbol from the 180. B, we're going to degrees, so we're going to multiply times 180 over pi. This time, instead of rewriting it, I'm just going to let my pi's cancel. So I'm left with negative 2 times 180 degrees all over 3. Now remember, the negative can go with the 2 or the 3. It's one or the other, but not both. So when I work this one out, I get negative 120 degrees. And then C here, again, it's in radians, so I'm going to go to degrees. So I'm going to multiply it by 180 over pi. My pi's will cancel, so I have negative 8 times 180 over 15. I'm going to multiply them out and divide it, and I get negative 96 degrees. Now for D, it's already in degrees, so we're going to change this to radians. Okay, so when you do this, be careful though, because unless it tells us to round to like 3 decimal places or something like that, it always wants us to leave the radian measure in terms of pi. So what I would get here, remember the 135s over 1, so I just have 135 pi over 180, and then we're just going to reduce that fraction, okay? So 135 divided by 180 is 3/4. And so we would put pi back on top with a 3. So we got 3 pi over 4. Okay, negative 320 degrees. Let's do the same thing. We're going to take it to radians. We're going to multiply by pi over 180. So we get negative 320 pi over 180. Reduce your fraction. Negative 320 over 180 is negative 16/9. So it's negative 16 pi over 9. And then our last one there, the negative 110 degrees, we're going to change it to radians, so multiply by the pi over 180. So the negative 110 pi over 180 reduces to negative 11 over 18. So we get negative 11 pi over 18. And then some practice with radians. It says how many radians is each angle of an equilateral triangle? Remember, an equilateral triangle has even angles, and so therefore each angle is going to be 60 degrees. But it wanted it in radians, so just convert it to radians then. So pi times pi over 180. So 60 pi over 180, and that's going to reduce to pi over 3. Now the minute hand of a clock travels how many radians in 15 minutes? So if you look at a clock, you know that if it's here at noon and it's here at the 15 minutes, that's just a 90-degree angle, right? And so you can convert it to radians. But then the next two also have the same kind of thing. So let's find this one a little different. Let's go ahead, we're going to find it using our radians. But remember, how many minutes are on the clock as we go around a full circle? Well, a full circle would be 60 minutes. So we're using 15 out of those 60 minutes of the complete circle. And I'm going to go ahead and put it in radians so we just have our answer. So if I'm using my calculator and I want to do this, don't put pi in it. So do 15 divided by 60 times 2, and it's going to tell you 1/4, and so we're going to put pi, it's going to tell you 1/2, and we're going to put pi back on the top there. So 1 pi over 2, or just pi over 2. All right, so using that same idea, the minute hand of a clock travels how many radians in 10 minutes? So we're going to take 10 over 60 of that full circle, so times 2 pi, and that's going to give us, if we take 10 over 60 times 2, it's going to tell us 1/3, and so we got 1 pi over 3, or just pi over 3. And then 4 there says the minute hand of a clock travels how many radians in 5 minutes? Well, now we're doing 5 out of 60 times the 2 pi. So 5 divided by 60 times 2 is 1/6. So we got pi over 6. Then at the bottom it says, what is the measure of theta in radians if x is equal to 45 degrees? All right, so we know x here is 45 degrees. So if you need to, go ahead and find what theta is in degrees first, okay? So theta in degrees, well, that's 45. I don't know why I put the degree symbol there. It's 45 degrees before the 360. So that 45 degrees is kind of like that reference angle, right? So this is going to be 315 degrees because we're going to take the 360 minus the 45, and that's going to give us the 315 degrees. Now, but it says, what is the measure of theta in radians? So now I'm just going to convert that. So I'm going to multiply that times pi over 180. And when I do that, I'm going to get 7 pi over 4. The 6 says, what is the measure of theta in radians? Again, well, notice this time they told us our theta is the same as the 5x, and then we have the other side over here that's just x. But we know that these two together form that straight line, which is either pi or it's 180 degrees. It doesn't matter which one you're going to use. Most of y'all are probably going to do degrees first, so I'll go ahead and do it in degrees, and then I'll show you what to do if you did radians. So we would say that the x plus the 5x made that 180 degrees. And so we could just solve for x. And so we would find that x is 30 degrees. But we know that theta is 5x. And so we would say 5 times 30, which is 150 degrees. But it wants it in radians. So multiply it times the pi over 180. And so 150 over 180 reduces to 5/6. So we got 5 pi over 6. Now that way took a little bit longer than if we'd have just done the radians to begin with, but I know that radians are a little tougher right now still for you. So if nothing else, we could have started out the same. We could have said, okay, Well, we know that these two angles here added together make that line, so we know that x plus 5x will equal, and this time I'm going to use radians, so pi. So that gave us that 6x is equal to pi, and so when we divide by 6, we find that x is equal to pi over 6. Then the same idea, well, theta was equal to 5x, so that's 5